Hi, this is Mrs. LaBarbara. This is Physics Chapter 10, Waves Intro, Video 3. Today's topic is the wave. The objectives are: know the definition of a wave, pulse, and medium. Know that all waves are produced by a vibrating source, and a wave has the same frequency as its source. Understand, wave transmit energy without transmitting mass. A wave's energy is represented by its amplitude. Understand that local particles in the medium only vibrates locally, while the wave travels from one place to another. Be able to determine the direction in which a particle will move in a medium as a result of its interaction with the wave. A wave is a series of vibratory disturbance. Some vibratory disturbance can only go through a medium. Others can go through both a medium or a vacuum. A vacuum is just empty space, has nothing, not even air in it. So over here, this is an animation of a wave. A wave is a series of vibratory disturbance. On the other hand, a pulse is a single vibratory disturbance that transfers energy but not mass. So here is a pulse, and here's a wave. A medium is just a matter, a body of matter in which the wave or pulse travels through. Let's take a look what that means. It's a little abstract. So the medium for the wave, in this case, for this wave, is the beads. Look like there is a string of beads. And this is kind of just like a rope or a string. There are other mediums that can be water. Without water, you can't have ocean wave, right? Without air, you can't hear me. Without people, there is no stadium wave. So for stadium wave to travel from one place to another, you need people, right? For the sound to travel from my mouth to your ear, you need air. So for the ocean wave to travel from the middle of the ocean to the beach, you need water or slinky, or there are many other mediums for waves to travel through. All waves are produced by a vibrating source. So a wave is started with a vibration, and its frequency, that means the wave's frequency, is the same as its source always. Doesn't matter what kind of wave it is. The vibration travels from one location to another. So take a look, this is a vibrator. So this vibration produces this wave. This vibration's frequency is your wave's frequency. Over here, this is electromagnetic waves are produced by vibrating charge, this right thing. So this wave's frequency is the same as the frequency of the charge moving back up and down. Here is kind of like a guitar string. So this is the source, vibrating chord. And this chord's frequency is the same as this sound's frequency. So sound wave is produced by a vibrating chord. And the frequency of the sound is the same as a vibrating chord. So over here it says radio wave is produced by accelerating electrons. So the radio wave has the same frequency as the electrons. Example, the diagram shows an antenna emitting an electromagnetic wave. In what way did the electrons in the antenna produce the electromagnetic wave? By remaining stationary, by moving at a constant speed upward only, by moving at a constant speed downward only, or by accelerating or alternately up and down. Let's see, a wave is produced by a vibrating charge. Vibrating means has to go up and down, so the answer is 4. Another example, how are electromagnetic waves that are produced by oscillating charges and sound waves that are produced by oscillating tuning forks similar? Both have the same frequency as their respective source. Both requires matter medium for propagation. Both are longitudinal waves, so both are transverse waves. We're going to talk about longitudinal waves and transverse transverse waves later, but now we have learned all waves have the same frequency as their respective source. So that is true for all waves. Next concept is wave transmit energy without transmitting mass or matter. So as a wave travels from one place to another, the energy of vibration is transferred from one place to another through the particle interaction in medium. However, the particle near the vibrating source does not travel with the wave from one place to another. Only the energy is traveled. And energy is represented by its amplitude. Let's take a look. So this vibrator going up and down. So this vibrator has energy. And this up and down motion is being transferred through this medium. The particles, as you can see, the beads next to the vibrator, that did not go from the beginning, from the left to the right. It's the energy, up and down motion is transferred. Same thing over here. So you're pushing these particles back and forth. This push is the energy. That push, the energy is transferred from left to right. But the particles over here next to this red object did not move from left to right. It's energy moved. So the energy again is represented by amplitude. So here are the two waves. The second wave has higher energy wave because it has bigger amplitude. Amplitude usually decreases. So wave usually loses amplitude. That's called a damping. When you lose amplitude, you lose energy. That you lost energy is due to friction as they travel. Check your understanding, true or false. In order for John to hear Jill, air molecules must move from the lips of Jill to the ears of John. This is false because wave transmit energy without transmitting mass. The matter in this, the mass here is the air molecules. Air molecule did not move from Jill's lip to John's ear because they could be rather far, but energy is transferred. Next one, Curly and Moe are conducting a wave experiment using a slinky. Curly introduces a disturbance into the slinky by giving it a quick back and forth jerk. Moe places his cheek at the opposite end of the slinky. Using the terminology of this unit, describe what Moe experiences as the pulse reaches the other end of the slinky. Well, Moe should experience the vibrating energy from Curly on his cheek. So only energy is transferred, not matter. Next concept is the direction of local particle vibrations and overall waves. So so far we have learned the wave is going from mostly from left to right. So as wave is passed from one side to another side, it could be from up and down, left to right also. So as a wave is passed from one side to another side, the local particles does not move from one side to another. Remember, only energy moved. How does a local particle move? Local particle only vibrates locally. Take a look. This is animation of stadium wave. This is a local particle. How does a local particle move? It only moves up and down locally. It doesn't go from left to right as the wave does. Here is another wave. So this is a local particle on the wave. You see that local particle? How is it moving? It only moves up and down locally. Here is another local particle. It only moves up and down locally. It doesn't go from left to right. Here is another one. Let's take a look at this particle. This is a wave. This is a different wave. It's like the sound wave we talked about. Here, the arrow is a local particle. The local particle only moves from left to right locally. It doesn't go all the way from the left to all the way from the right. Only left and right locally. So local particle only moves locally as wave from one place to all the way to the other place because wave transfers energy, not matter. Now we know local particle moves only locally, but which way does it move? What is the direction of motion of a particle in the medium? As the wave travels to right or to left, a single point on the wave on the medium only moves up and down for this type of wave, for the sine wave. To determine the direction of particles' motion, we simply just have to draw the wave in the next instant in the direction of motion to find out where it's moving. Take a look, here is a wave, and it tells you the wave is moving to the right. So you draw the wave to the right in the next instant. It would look like this. And where is this particle going to go? So since the red one is below it, so that's where the particle going to be part of the new wave. And this particle is going to move upward because the red wave, the new wave, is above it. And this particle is going to move downward because the new wave at that point is below it. Similarly, if this wave is moving to the left, we simply draw a new wave going to the left. And where is this particle going to move? It's going to move down because new wave is below it. This particle is going to move up because new wave is above it. And this particle is also going to move up because new wave is above it. That's how we determine the direction motion of a particle in the medium. Let's do some practice. As shown in the diagram, a pulse moves along the rope in which direction will segment X move as the wave passes through it. Since the wave is moving to the right, let's do it slowly and pay attention to that point. Whoops. It's moving to the right, not moving. Now it has to move up, then moves down. So the X has to move up, then down. Another example, the diagram shows a pulse moving in the direction shown by velocity vector v at the instant shown. A quark at point P on the water surface is moving in which way? So this dashed line is a new wave because that's the wave going to the right. At this point, the wave is above P, so the quark is going to move upward. Another example, the diagram below represents a transverse wave traveling to the right through the medium. So point A represents a particle in the medium. In which direction will particle A move in the next instant of time? So the wave is going to the right, so you draw a wave going to the right. And at the next instant, the A has to come down because that's where the new wave is. So the answer is downward. That's it for today. Thanks for watching.